In preparation for exam 2, I'm just going to go through a few things that you need to know. We have already covered organometallics, and under that heading, we've covered Grignard reagents, how to make Grignard reagents. We've also talked about using Grignard reagents and coupling reactions with alkyl halides and with carbonyls like aldehydes, ketones, and esters. We talked about the Gilman reagent, which is the cuprate. Talked about how to make those from organolithium reagent and how we can use those in coupling reactions also with alkyl, aryl, and vinyl halide. We also discussed substitution and elimination mechanisms, and what you need to know is the rate laws for the different types, the bimolecular as well as the unimolecular. The different arrow pushing mechanisms, like for SN1, the leaving group leaving first, and then the nucleophile attacking the carbocation intermediate. The ICE method, remember, identify, characterize, and then execute. We have videos for each one of these topics, so you should go back and check those videos out while you're studying. A good place to also look is the syllabus. The syllabus has problems for each section that we're going to cover on the exam. Also, the last topic we talked about is conjugated dienes. I'm going to go through an example toward the end of this video, and you need to be able to identify the molecular orbitals for 2-pi, 4-pi systems, identify the HOMO and LUMO, and identify the thermodynamic and kinetic products of addition of HX, where X is a halogen. So let's get into this. Just a review of organometallics. Remember, if you take a ketone or an aldehyde, first treat it with a Grignard and then treat it with acid or some type of proton source. What do you get? You get an alcohol. Remember, this carbon in the carbonyl is partially positive, and so because of that, the carbon in the Grignard that's connected to magnesium is partially negative, and so that attacks here, and then eventually you get the alcohol as the product. You can look back in your notes if you want to see the mechanism for that, because we went over that on multiple occasions. So just remember that a Grignard plus an aldehyde or a ketone followed by H plus, right? Remember, you don't want to ever expose the Grignard to H plus because it'll destroy it, but you treat the ketone or aldehyde with the Grignard and then you follow it up with H plus, and then you always get an alcohol in the product. By the same token, if you take a Grignard and an ester, what do you get? You get a ketone where the group that's attached to the Grignard, so the organo part of the organometallic, remember, this is the metal, this is the organic part, so this group is what gets transferred here, right? And again, we've gone through this mechanism. You need to go back and look at it, but you get a ketone in the product, right? So remember, a Grignard plus an ester always yields a ketone. So you need to go back, look at the videos for Grignard and Gilman reagents. Those are on YouTube under organometallic. All right, so now let's talk a little bit about substitution reactions, substitution and elimination reactions. Remember, we studied 4 different mechanisms: SN2, SN1, E2, and E1. SN2 and E2 are both bimolecular, meaning that the rate is dependent on the substrate as well as the nucleophile in the case of SN2, or the substrate and the base in the case of E2. Remember, E2 requires a strong base. For SN1, this was unimolecular, and then E1 was also unimolecular, and the rate law is the same, K times the concentration of the substrate. So how is this important? Well, we need to know this in terms of changing up the different substrates or the nucleophile. In the case of SN1, if I change the nucleophile concentration, nothing happens to the reaction. But if I look at the SN2 mechanism, if I change the nucleophile concentration, then the rate is also going to change with that. So those are just some things to think about. You need to know the rate laws because there'll be some questions on the exam dealing with the rate law. Let's apply this, and again, with these SN1 and SN2 mechanisms and E2, E1, I gave you what was called the ICE method. So you identify, meaning that you go and look at your substrate, you look at your nucleophile, your solvent, And if you have the products, you look at the products, right? So using the ICE method, let's identify. So we have an allylic substrate, a very good leaving group with the tosylate. We are in a protic solvent, and then we have a pretty good nucleophile, and then we get a racemic mixture of products. So which mechanism would this particular reaction be going through? It's got to be going through the SN1 because of the benzylic substrate. Remember, that can do SN2 or SN1, but in this case we're in a protic solvent, so it's more than likely going to do SN1. And then the products are racemic, which is also characteristic of the SN1 mechanism. Notice we started out with an alcohol, and then we ended up with an alkene, and we're doing this in sulfuric acid, which is a proton source. So this is protic. What mechanism is this going through, right? Well, if we look at the rate law, rate is K times the substrate. So we know that this has to be going through an E1 mechanism, because you know it's an elimination because you have a double bond in the product. But we started with a secondary alcohol. Remember, secondary can be SN1 or E1, unimolecular. We have a protic solvent, and that we're using sulfuric acid. And we also have an alkene in the product. So here's another example. If I treat iodocyclohexane with the azide anion, and I do this in DMF, notice what happened. The iodine got replaced by the azide, and then I have iodine here. So iodine is obviously my leaving group. What mechanism did this reaction undergo? Well, it has to be SN2, because first of all, I have a secondary substrate. That can be either or. It can be SN1 or SN2, but then I'm doing this reaction in a polar aprotic solvent with a good nucleophile. This particular reaction happened through an SN2 mechanism. And again, here's the rate law. Rate is K times the concentration of the substrate and concentration of the nucleophile. And so because of that, we know that this particular mechanism was SN2. Let's look at this reaction where we can clearly see that OH is deprotonating. These electrons are coming here to make a double bond, and then bromine is leaving. So these are my products, with the double bond being my major product, and this is being done in DMF as a solvent. And so obviously this is an E2 mechanism, elimination because of the double bond in the product, but this is a primary substrate. We're in a polar aprotic solvent, and we'll have a very strong base in that this could be sodium hydroxide or potassium hydroxide. All those are pretty strong bases. And so knowing that, this is the strategy that you have to employ when you're trying to determine the type of mechanism. So you use the ICE method. You identify your substrate, you identify your nucleophile or base, you identify your leaving group, and then you can also look at the products to see what the outcome of the reaction was, and then you can make a decision. That's the execution part. You make a decision on what mechanism actually happened. All right, so now last thing that we reviewed in class was dealing with conjugated dienes, and we talked about the 2-pi system, which is fairly simple. You can go back and watch that video again. The 4-pi system we discussed also, where remember we talked about the 4 molecular orbitals being an outcome of having a conjugated 4-pi system, where you have a diene with 2 double bonds and 4 p orbitals. And then we also talked about the standing wave theory, dealing with molecular orbital theory, in that the first harmonic, the wave never passed through 0, so the sign of your orbitals never changed. And then in the second harmonic, the wave passed through once. And in the third harmonic, the wave passes through twice. And then the fourth harmonic here, the wave passes through 3 times. You'll notice that the signs are alternating. And so what does this mean in terms of the 4-pi system? Well, first of all, let's talk about the electrons. You have to fill these molecular orbitals just like you would any other orbital, in that you put 2 electrons in one orbital before you put 1 in any of them. That's Hund's rule. And so here you fill it 2 electrons here and 2 here. This becomes the HOMO, or the highest occupied molecular orbital, and then the orbital above it, because it's empty, becomes the lowest unoccupied molecular orbital. We had some trouble with this in class, but these 2 are unoccupied here, but this orbital is much lower in energy than this one, and so this is the lowest unoccupied. here these two are both filled, but this orbital is higher in energy than this orbital, and therefore this is the highest occupied. So how do we translate this? If we bring in the diene, you can see that, you know, this is what this means. So here's my diene. Here is the first set of molecular orbitals. Here's the second set. Here's the third set, and here's the fourth set. What matters in this case is that how this thing reacts, right? The molecular orbitals are going to determine how the diene actually reacts. And so it's either going to react through the HOMO or the LUMO. And that's what we want to take away from this whole discussion about HOMO, LUMO, and conjugation, is that this particular diene is only going to react through either its HOMO or its LUMO, and that's going to depend on the role of the diene. If it's acting as a nucleophile, obviously it's going to be donating electrons, so it's got to react through the HOMO. If it's acting as an electrophile, then it's got to accept electrons, and so it's going to react through the LUMO. And so one reaction, we're not going to cover cycloaddition, but on the exam we're going to talk about addition of HX to a conjugated diene, and I sent this video before and we didn't have a chance to discuss it, so I'm going to just talk a little bit more about it here. So again, this diene is going to attack HBr. You can see the arrows here. You see H is added to this carbon, and then my positive charge is here, right? This is the key characteristic for addition of HX to a diene, is that you form an allylic carbocation. Remember, allylic means adjacent to a double bond, and this is the only carbocation that's formed. You never form the non-allylic carbocation, right? So from the carbocation, bromine can attack here or it can attack here, right? We call this one 1,2 addition because if we start numbering here, 1, 2, 3, 4, and the plus charge is on carbon number 2, then bromine attacks directly at carbon number 2. If bromine attacks at the 4 carbon and shifts the double bond over, then we get this product, and this would be called 1,4 addition. The key about this particular reaction is that it's temperature dependent. So the product distribution, whether you get the 1,2 or the 1,4 product, is going to depend on the temperature. The 1,4 product is more difficult to form, and so at higher temperatures this is going to predominate. The 1,2 product is a little bit more easily formed because it's easier for bromine to attack directly at the plus charge. So if that's the case, at low temperatures, the 1,2 product is going to dominate. So how do we apply this to an example? All right, so here's my conjugated diene. I can react through either one of these double bonds, but for simplicity, we're going to react through this double bond. Right? At low temperature, what product do I get? Well, first let's look at what happens, right? If this double bond attacks HBr, then I'm going to get this carbocation intermediate, where the H from HBr adds to this carbon. You see that here now, this is a CH3, and then this carbon becomes positively charged. Now, at low temperatures, what would the product be? Well, low temperatures favor the 1,2 product. And so if that's the case, at low temperature, bromine comes in, bromine attacks at the plus charge directly, and then I get the 1,2 product, right? That's at 0 degrees Celsius. At 40 degrees Celsius, I should get a different product, and I will get a different product. At 40 degrees, that's higher temperature. Bromine comes in, bromine attacks at the 4 carbon here and shifts the double bond over. And so if that's the case, then I get this as a product where bromine has done 1,4 addition. All right, so on the exam you need to be able to distinguish between on the exam you need to be able to distinguish between the temperature differences and which product predominates. So at low temperature you get the kinetic product because it's formed the fastest. At higher temperatures you get what's called the thermodynamic product, because even though it's a more stable product, it's not formed as fast. Alright, so if you have any questions, I'm going to open a discussion board on Blackboard, and feel free to post questions, and even tomorrow night I'll be willing to open a chat and have a dialogue about this exam. So I'll see you on Monday, and if you have any questions, just let me know.